When we read modern code, we experience it visually. We see color-coded syntax, organized indentation, and structured blocks that make human-readable sense. The hardware ignores these formatting cues. To a computer, source code arrives as a flat, continuous, one-dimensional stream of bytes. This creates an immediate architectural problem. A compiler cannot verify logic, check data types, or generate executable machine code from an unstructured string of characters. To breach this gap, the compiler pipeline begins with a strict initial phase, lexical analysis, often called scanning. The lexical analyzer serves as the compiler's text processing gatekeeper. Its sole purpose is to organize this raw string of characters into distinct, manageable logical units before any true computation or logical evaluation begins. Why insert an entirely separate phase here? Why not program the compiler's parser to evaluate the raw text directly? Designing a compiler requires a strict separation of concerns. The physical processing of a text file must be isolated from the evaluation of grammatical rules. The lexer acts as an insulating layer. It absorbs the heavy input-output operations, buffering the data, and handling all the hardware-specific quirks involved in reading text files from memory. By aggressively stripping out whitespace, line breaks, and comments before the parser is invoked, the lexer reduces the total volume of data that needs to be analyzed. This abstraction boundary guarantees the parser remains unburdened by text formatting. It leaves the parser free to focus entirely on recursive grammatical rules, operating on a clean, pre-categorized stream of data. To see exactly how this extraction works, consider a simple assignment statement. Position equals initial plus rate times 60. The lexer evaluates character blocks sequentially. To track its place, it uses a two-pointer system. Lexin begin anchors the start, while the forward scanning head advances character by character until it detects a logical boundary, the first blank space. Once that boundary is confirmed, the lexer discards the white space. Because these characters hold no logical value for the computer, they are stripped from the processing queue immediately. The sliding window creates a vacuum. It strips away everything intended for human readability, leaving behind the raw elements of computational intent. The isolated characters form our first data structure, the lexium. The lexer evaluates this against a pattern, a programmatic rule like a regular expression. The word position perfectly satisfies the identifier pattern and is packaged into a token, the abstract tuple ID1. The first half of this tuple is the token name. By passing this, the lexer tells the parser the broad categorical type of the unit it just processed. The second half is the attribute value. The parser must know which specific identifier this token represents in order to evaluate the program's logic later on. Through this triad, the physical lexeme, the validating pattern, and the output token, the lexer converts a character string into a standardized data structure. To manage all these specific identifiers, the compiler relies on a primary ledger called the symbol table. It stores the names, types, and scope of all discovered variables. As this diagram illustrates, the attribute value 1 is not a mathematical integer. It is a precise memory pointer directing the compiler to the symbol table entry specifically created for the variable position. Now the theoretical read head advances to the equal sign. When evaluating an operator, the lexer typically outputs a token without an attribute value. A tuple containing just the equal sign carries all the necessary grammatical information the parser needs. Skipping ahead to the final term, the read head captures the characters 6 and 0 and successfully matches them against the pattern for a numeric constant. For a constant, the token often skips the symbol table entirely, using the numerical value itself directly as the attribute, formatted as number, 60. By standardizing infinite variations of variables, operators, and constants into uniform tuples, the lexer flattens human text into a tightly controlled vocabulary. This rigid pattern matching system works on correct code, but how does it handle a broken string? Consider this block of C code where a programmer has typed fi instead of the conditional if. The lexer checks the characters against the keyword pattern for if and rejects it. However, a letter followed by another letter matches the broad pattern for an identifier. The lexer emits an ID token for fi without triggering any warnings or errors. This exposes the architectural limit of the phase. The lexical analyzer is context blind. It is a local pattern matcher. incapable of determining if a valid sequence of words actually makes grammatical sense. The compilation will still fail, but that failure occurs in the next stage. The parser will receive an ID token in a location where its strict grammatical rules demand a conditional keyword, and it will halt the process. A true lexical error only occurs when a sequence of characters matches 0 known patterns, such as the sudden appearance of an illegal special character. When that happens, the lexer usually initiates a basic panic mode recovery. It deletes characters until finding a valid pattern, leaving the ultimate failure state to the parser. The lexical analyzer performs the mechanical heavy lifting. By organizing human text into a structural vocabulary, it enables the machine to process meaning and logic in the stages that follow.